Hello and welcome back. In this video, we're overclocking the Ryzen Threadripper 5990X all the way up to about 4.8 GHz using EK Quantum water cooling and the ASUS ROG Zenith 2 Extreme Alpha motherboard. To be more precise though, we're overclocking an early engineering sample of what was supposed to be the successor to Ryzen Threadripper 5990X. As you undoubtedly know, AMD never ended up releasing the consumer versions of the Zen 3 Threadripper. Anyway, as this is an early engineering sample of an unreleased CPU, I'll try to cover the overclocking challenges as detailed as possible. Do note that there's going to be quite a bit of challenges, so it's going to be a longer video, but I hope you still enjoy it. Alright, let's get started. First of all, the Ryzen Threadripper 5990X doesn't exist. Even though AMD announced the Ryzen Threadripper 5000WX series back in March 2022, it never announced the consumer variants of Ryzen Threadripper 5000. But that doesn't mean that it never planned for them. Over the past couple of months, I've gathered information on the elusive consumer Threadripper 5000 processors. Based on my findings, early engineering samples were available and tested by AMD board partners back in June 2021. Validation samples of the final silicon were supposed to be available in September 2021, with the formal product launch 1 or 2 months later. However, those validation samples never arrived at the board partners, and as we now know, the product launch never took place. Instead, it appears that AMD has entirely abandoned the consumer variants of Ryzen Threadripper and just focuses on the professional variants. We'll get back to that later, but first, let's talk about the origin story of Ryzen Threadripper. As the story goes, the original Ryzen Threadripper was greenlit by AMD executives despite having no business plan other than making something that was awesome. The Threadripper slid in between the 8-core Ryzen 7 1800X and the 32-core EPYC 7601 in core counts and effectively completed AMD's industry-disrupting product lineup. At the end of the day, however, a business needs to make money. While the original Ryzen Threadripper was positioned as the ultimate platform for PC enthusiasts, gaming performance was somewhat troublesome. In addition, AMD realized that the business case for Ryzen Threadripper lies not with gamers or enthusiasts as upmarket from Ryzen, but rather with professional workloads as downmarket from EPYC. And thus, the slow repositioning of Ryzen Threadripper began. The Threadripper WX product was first introduced in 2018 when AMD announced the second generation Ryzen Threadripper processors. AMD tried to clearly separate the X series from the WX series. WX is designed for creators and innovators, whereas the X series is for enthusiasts and gamers. WX series get up to 4 CCDs and 32 cores, whereas X series get up to 2 CCDs and 16 cores. WX series processors have a TDP of 250 watt, whereas the X series processors have a TDP of 180 watt. However, fortunately, both WX and X series processors were compatible with the consumer X399 chipset motherboards. The next generation of Ryzen Threadrippers took that segmentation one step further, as now the consumer and the professional variants of the Threadripper CPU have a separate socket and a separate chipset. Together with the Zen 2 based Ryzen Threadripper processors, AMD introduced socket TRX4. TRX4 is the direct successor to and mechanically compatible with the TR4 socket used for the first and second generation Threadrippers. However, it is electrically incompatible, meaning third generation Threadripper requires a new motherboard. Unlike their SP3 server counterparts, TRX4 processors require a chipset to work. On November 25, 2019, AMD announced the Ryzen Threadripper 5990X, the world's first 64-core consumer processor to accompany the TRX40 chipset. In July 2020, AMD launched the Threadripper Pro WX processor series, which requires the WRX8 socket and WRX80 chipset. The Threadripper Pro WX line is much more clearly a downmarket equivalent of the EPYC server processors, as they offer the same 8-channel memory and 128 PCIe lanes. That brings us back to the Zen 3 based Ryzen Threadripper 5000 series we discussed earlier. While both consumer and professional variants were on roadmaps initially, in the end, AMD decided to only launch the professional Ryzen Threadripper Pro WX product line. We can only speculate about the exact reasons why this decision was made. Linus Tech Tips did a pretty good job of summing up the possible causes. They range from the profit-greedy
evil corporations
argument to
the high-end desktop concept for enthusiasts is currently obsolete.
We can add to that pandemic-related supply chain constraints, a surge in PC demand, and no competition in that particular segment. So then the business case becomes very clear. If there's no need to innovate in a certain segment and you can use your Zen 3 chipsets somewhere else, why wouldn't you? However, as Linus points out correctly, the Threadripper series also provide AMD with low-hanging marketing fruit that can help improve
mindshare.
As the Threadripper series have proven repeatedly, having extreme overclockers push the chips to their limit provides an endless stream of performance world record media coverage. And that's where the Threadripper 5000 story gets a little funky. While AMD has abandoned the consumer variants, it hasn't abandoned Threadripper overclocking. Just one day before recording this video, AMD confirmed that overclocking would come to the Threadripper Pro series. Now, it's great that AMD is still looking to enable overclocking support, but unfortunately, I think they didn't plan that all too well. What you need to know about motherboard companies is that the consumer team is usually different from the workstation team. And while the consumer teams are typically happy to accommodate overclocking features, even if it's a low volume showcase, the workstation teams are typically not. In fact, when AMD presented the opportunity to enable overclocking for Threadripper Pro and WRX 80, some motherboard vendors outright refused to develop the solutions. Anyway, let's get back to the CPU I'm supposed to be overclocking in this video. This Ryzen Threadripper 5990X engineering sample sports 64 cores and 128 threads featuring the Zen 3 core architecture. It has a base frequency of 2.5 GHz and boosts up to 4.45 GHz. The TDP is 280 Watt. In this video, I'll cover 4 distinct overclocking strategies. First, we enable Precision Boost Overdrive 2 and enable DOCP. Second, we tune the Precision Boost 2 parameters with Curve Optimizer. Third, we will manually tune the Precision Boost Overdrive 2 electrical and thermal parameters to their limits. Fourth, we push the PBO 2 parameters to their absolute limits. Lastly, we go for a couple of manual overclocks. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that I'll be using in this guide. Along with the AMD Ryzen Threadripper 5990X ES processor and the ASUS ROG Zenith 2 Extreme Alpha motherboard, in this guide we will be using 2 pairs of 16GB G.Skill Trident Z DDR4 4266 memory sticks, a 120GB Kingston KC400 SSD Now SSD, an NRMax Max Revo 1500 watt power supply, the Elmo Labs Easy Fan controller, the Elmo Labs power measurement device, the Elmo Labs EVC2, an EK Quantum Momentum monoblock, and EK Quantum water cooling. All this is mounted on top of our favorite open bench table V2. The cost of the components should be around $8,833. Regular viewers of this channel will notice that the hardware selection is very similar to the one that I used in SkatterBencher number 36 when I overclocked the Ryzen Threadripper 5990X. In that video, I highlighted a bunch of challenges and constraints related to overclocking a 64-core Ryzen Threadripper CPU. So in this guide, I'm trying to address all of those challenges as well as a couple of new ones that popped up. As was the case with the 3990X, and as you'll find out in this overclocking guide, the Ryzen Threadripper 5990X draws a lot of power and current at full blast. Therefore, I also stick with the NRMax Max Revo 1500 watt power supply, which I used for the 3990X. The Max Revo offers up to 30 amps on 4 of the 12-volt rails and up to 125 amps for all 12-volt rails combined. This power supply was more than sufficient for my Ryzen Threadripper 5990X, and it was also sufficient for this 5990X. Obviously, the CPU temperature will be a challenge. Contrary to the 3990X system, I will not use EK's flagship Magnitude SDRX4 water block. Instead, I will use EK's Quantum Momentum monoblock for the Zenith 2 Extreme Alpha motherboard. The CPU cooling engine is based on the previous generation Velocity SDR4 design, which was designed specifically for multi-chiplet CPUs like the Ryzen Threadrippers. I don't expect the performance to be as good as the Magnitude, but it should still be more than good enough to squeeze more performance out of this CPU. A challenge that I didn't explicitly highlight with the 3990X and the Zenith 2 Extreme is the VRM temperature. However, as you'll find out in this overclocking guide, this Zen 3 Ryzen Threadripper is pushing the VRM of the Zenith 2 Extreme Alpha to its absolute limit. Without the help of active liquid cooling, we'd have serious overheating issues. In fact, I think it's about time that both CPU makers and motherboard makers start thinking about liquid cooling first designs. Of course, there are already many liquid-cooled motherboards on the market. Still, more often than not, these designs prioritize aesthetics over performance or cost. CPUs like the Ryzen Threadripper, especially the overclockable ones, pack a tremendous amount of performance that can only be reliably unleashed using liquid cooling. As I highlighted in SkatterBencher number 36, where I overclocked the Ryzen Threadripper 5990X, the water temperature was a crucially limiting factor of my overclock. As per usual, I used the Elmo Labs EFC to control the radiator fans and regulate the water temperature. Without going into too many details, I have attached an external temperature sensor from the water in the loop to the EFC. Then I used the low-high setting to map the fan curve from 25 to 40 degrees water temperature. That means the curve initiates the fan at 25 degrees Celsius and ramps up gradually to 100% fan speed at a water temperature of 40 degrees Celsius. With regular desktop CPUs, the CPU temperature reaches TJ max well before my fans run at 100% due to the water temperature. However, with the Ryzen Threadripper 3990X under a sustained multi-threaded workload with PBO enabled, the water temperature exceeds 40 degrees Celsius. That means even though my fans are spinning at full blast, they're not able to cool down the radiator and water sufficiently. As promised, I upgraded the cooling solution for the Ryzen Threadripper 5000 series processor. In addition to my usual EK Coolstream PE360 radiator with 3 EK Vardar Evo 120ER fans, I added an EK Quantum Surface P480M with 4 EK Furious Meltemi 120 fans. This cooling solution worked perfectly, as during my testing, the maximum water temperature that I spotted was about 37 degrees Celsius, still below my maximum temperature of 40 degrees Celsius. However, it's close enough that the fans spin up quite high and the noise is nearly unbearable, so I wouldn't quite recommend it for a daily system. We use Windows 11 Enterprise and the following benchmark applications to measure performance and ensure system stability. Regular viewers of this channel will know that this is identical to the software stack we used in SkatterBencher number 36 with the Ryzen Threadripper 3990X. I suggest you check out that video to understand some of the challenges related to benchmarking the 64-core Ryzen Threadripper processors. Before we start overclocking, first let's check the performance at default settings. A couple notes though. One, since this is an engineering sample of an unreleased processor, you should take the stock performance with a grain of salt. The final specifications and performance may have differed significantly from what I obtained. I used the stock benchmark results as a baseline to measure the performance increase after overclocking. 2. The ROG Zenith 2 Extreme Alpha motherboard enables Precision Boost Overdrive by default. So to check the performance at stock settings, you first have to go into the BIOS and go to the AI Tweaker menu, enter the Precision Boost Overdrive submenu, set Precision Boost Overdrive to disabled, then save and exit the BIOS. Here's the benchmark performance at stock. When running Prime 95 small FFTs with AVX enabled, the average CPU effective clock is 2276 MHz with 0.73 volts. The average CPU temperature is 45.8 degrees Celsius. The average VRM temperature is 31.9 degrees Celsius. And the average water temperature is 27 degrees Celsius. The average CPU package power is 218 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 2420 MHz with 0.76 volts. The average CPU temperature is 46.2 degrees Celsius. The average VRM temperature is 31.9 degrees Celsius. And the average water temperature is 27.1 degrees Celsius. The average CPU package power is 224.9 watts. Going forward, I will try to simplify the Prime 95 reporting, so I will just highlight the differences rather than explicitly stating all the different values. As we learned with our Ryzen Threadripper 5990X, Windows and some benchmark applications don't scale very well when SMT is enabled. So from a performance tuning perspective, it makes sense to see if disabling SMT can provide us with additional performance in our specific applications. To run stock with SMT disabled, you first have to go into the BIOS and go to the AI Tweaker menu, enter the Precision Boost Overdrive submenu, set Precision Boost Overdrive to disabled, go to the Advanced menu, enter the CPU configuration submenu, set SMT mode to disabled, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Similar to the Ryzen Threadripper 5990X we tested before, some benchmark applications perform better when we disable SMT. Most notably, we see a plus 25% performance uplift in Y-Cruncher Pi and a plus 21% uplift in Geekbench 5. However, in some benchmarks, we see a performance downgrade. For example, our Blender Classroom performance is down 8%. When comparing the Prime 95 results, we find that disabling SMT for both AVX and non-AVX workload scenarios provides additional performance headroom. The Precision Boost algorithm boosts the frequency 222 MHz higher in an AVX and 315 MHz higher in a non-AVX all-core multi-threaded workload. That's because disabling SMT allows for additional voltage headroom within the Precision Boost limits. This extra voltage headroom then translates into higher clock frequencies. Important to note is that both the TDC and EDC parameter are at their limit of 215 and 300 amps respectively. These limits are conservative as the maximum PPT remains well below the TDP limit of 280 watts. In other words, the limitation of the system is not the CPU TDP, but the AMD configured VRM limitations. Of course, we can override these limitations using Precision Boost Overdrive, and that's what we'll do in our first overclocking strategy. In our first overclocking strategy, we simply take advantage of enabling Precision Boost Overdrive and ASUS DOCP technology. With the launch of the Zen 3 architecture, AMD also released a new version of Precision Boost Overdrive. It's called Precision Boost Overdrive 2. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost Override and Scaler, Precision Boost Overdrive 2 introduces Curve Optimizer. There are essentially three levels of Precision Boost Overdrive. 1. AMD's stock values, which can be set by disabling PBO. 2. The motherboard vendor values, which are programmed into the BIOS to match the motherboard VRM specification and can be set by enabling PBO. And 3. End-user custom values, which can be programmed by the end-user themselves. I explored the ins and outs of Precision Boost Overdrive 2 tuning in my Ryzen 7 5700G SkatterBencher video. If you want to learn more about the impact of each of these settings, I suggest you check out that video. In this overclocking strategy, we simply enable Precision Boost Overdrive, whereas in future strategies, we'll actually go in and tune some of the parameters. When we enable Precision Boost Overdrive, we actually just rely on the pre-programmed values in the motherboard BIOS. We find that the following values have changed. PPT limit from 280 watt to 600 watt, TDC limit from 215 amps to 400 amps, EDC limit from 300 amps to 470 amps, and the FIT limit from 2024 to 14,171. Increasing the PPT and especially the TDC and EDC limit will help unleash the frequency and multi-threaded workloads previously limited by the EDC. The CPU fit limit increases by changing the scalar and encourages the CPU to pursue higher voltages. The frequency limit can technically also increase using a plus 200 MHz boost override, but this is not done with this particular BIOS. The THM, temperature, and VID, voltage limits are hard-coded and cannot be manually increased. DOCP stands for Direct Overclock Profile, and it's an ASUS technology that aims to mimic the behavior of Intel XMP technology. XMP allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports XMP, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. While my memory is rated at DDR4 4266, I choose to run it at DDR4 3600 with the fabric clock in sync at 1.8 GHz. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP standard. Set memory frequency to DDR4 3600 MHz. Set F-clock frequency to 1800 MHz. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation with both SMT enabled and disabled. We get significant performance gains in all multi-threaded benchmark applications by simply enabling Precision Boost Overdrive. The highest performance increase is in 3DMark CPU Profile Maxed threads with plus 44.26% over stock performance. We also get a slight improvement in tests that only use a few cores thanks to the increased DRAM and fabric clock frequency. In Prime 95, simply enabling Precision Boost Overdrive gives us a ridiculous performance improvement across the board. Across all Prime 95 configurations, SMT, no SMT, AVX, no AVX, we get an additional 1 GHz of performance. With SMT enabled and AVX disabled, we even get almost 1.2 GHz higher frequency. That's insane. If you remember, the performance uplift from enabling PBO on the 5990X was only about 700 MHz. Another thing to note is that while the CPU temperature increased to about 70 degrees Celsius, the limiting factor is neither the CPU, the VRM, nor the water temperature. However, as in our stock configuration, we are limited by the PBO VRM configuration. Specifically, we reach the maximum allowed EDC of 470 amps in every single of our Prime 95 tests. In our second overclocking strategy, we use the brand new feature of PBO 2 called Curve Optimizer. As I mentioned, Curve Optimizer is a key new feature of Precision Boost Overdrive 2. Curve Optimizer allows end users to adjust the voltage frequency curve for each CPU core separately. You can offset the entire curve by up to 30 steps in either a positive or negative direction. Each step represents between 3 and 5 mV, so quick math tells us we can increase or decrease the curve by up to 150 MHz. When you adjust the voltage frequency curve with a negative point offset, two things happen. First, you effectively tell the CPU that for a given frequency it needs less voltage, and as a consequence, at a given voltage you can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. As I mentioned already, Curve Optimizer is supposed to be available on a per core basis. I was kind of looking forward to spending a couple of evenings trying to curve optimize every of the 64 cores available on this Ryzen Threadripper CPU. Unfortunately, on this beta BIOS, only the all-core curve optimizer setting is available, so I couldn't tune every core independently. I did try flashing a public BIOS, but then the system didn't boot up, so all-core curve optimizer was the only setting that I could use. For this overclocking strategy, I use a curve optimizer setting of -15. While up to -30 worked in most benchmarks, it didn't pass Prime 95 stability testing. In addition to Curve Optimizer, compared to the previous overclocking strategy, I also changed the Fmax override from 0 MHz to 200 MHz and the scaler from 7x to 10x. Fmax override, also called Max CPU Boost Clock Override, simply increases the arbitrary clock frequency ceiling. On AMD Ryzen CPUs, you can raise the ceiling up to 200 MHz in steps of 25 MHz. Scaler is a tool that allows users to increase the FIT limit. FIT stands for failures in time and is a standard reliability metric in the semiconductor industry. One FIT is defined as one failure every billion hours of operation. Every CPU has a specified FIT value from the factory, and the scaler allows you to manually increase that value. On this particular CPU, the standard FIT is 2024, and when applying the 10x scaler, the FIT becomes 20,244. The Precision Boost algorithm will consider the FIT limit to evaluate the voltage headroom. With a higher allowed FIT, the CPU will allow for higher voltages to be used despite potentially harming the lifespan of the CPU. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP Standard. Set memory frequency to DDR4 3600 MHz. Set F-clock frequency to 1800 MHz. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Go to the Advanced menu. Enter the AMD Overclocking submenu. Click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set Precision Boost Overdrive Scaler to Manual. Set Precision Boost Overdrive Scaler to 10x. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 15. Leave the Curve Optimizer submenu. Set Max CPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation with both SMT enabled and disabled. The combination of an increased Fmax and using Curve Optimizer should impact the fewer threaded applications more than the multi-threaded applications. We see improvements in those benchmarks by up to 8% in, for example, Geekbench 5 single. In multi-threaded applications, we also marginally improve our performance up to plus 45.92% in 3DMark CPU Profile Max threads. Using Curve Optimizer allows the CPU to use less voltage for a given frequency and thus potentially boost to higher frequencies with a given voltage. We see an improvement of about 100 MHz in Prime 95 stable frequencies with similar or slightly lower effective voltage. In our third overclocking strategy, we will manually tune the Precision Boost Overdrive 2 electrical and thermal parameters. As you definitely know by now, Zen 3 processors like the Ryzen Threadripper 5000 series come with the Precision Boost Overdrive 2 toolkit. This toolkit allows you to manually tune some of the parameters of the Precision Boost algorithm. We used several manual tools to get higher frequencies in the previous overclocking strategies. However, we still relied on values pre-programmed in the BIOS to work around some power and electrical limitations. Looking at the Prime 95 results from OC strategies 2 and 3, we find that our system is still hitting limits. In all test scenarios, we hit the EDC limit of 470 amps and got very close to the TDC limit of 400 amps. Prime 95 is not the only application we find our CPU hitting the ceiling. When we monitor the behavior in each of the benchmarks, we hit the EDC limit in Geekbench 5, Cinebench R23, CPU-Z, Y-Cruncher, and Blender. We can get around these limits by manually tuning the Precision Boost Overdrive 2. Simply go into the BIOS and gradually increase the limits until you find your benchmark applications no longer being bottlenecked by any of the parameters. With regular Ryzen CPUs, you'll find that eventually the limiting factor for the CPU becomes either the maximum precision boost frequency limit or the CPU temperature. However, the 64-core Ryzen Threadripper 5990X is a whole different beast. The combination of high voltage but low power for single-threaded applications and low voltage but high power for multi-threaded applications is really tough on the VRM. And we find ourselves being critically limited by transient currents, going from a low load to a high load. Practically, we have to limit the EDC to 800 amps. If we don't, the VRM will shut down when running Y-Cruncher, AI Benchmark, or initializing Prime 95. So, after tuning, I use the following PBO settings. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP Standard. Set memory frequency to DDR4 3600 MHz. Set F-clock frequency to 1800 MHz. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to manual. Set PPT limit to 1000. Set TDC limit to 800. Set EDC limit to 800. Set Precision Boost Overdrive Scaler to manual. Set Precision Boost Overdrive Scaler to 10x. Set Max CPU Boost Clock Override to 200 MHz. Go to the Advanced menu. Enter the AMD Overclocking submenu. Click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set Precision Boost Overdrive Scaler to Manual. Set Precision Boost Overdrive Scaler to 10x. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 15. Leave the Curve Optimizer submenu. Set Max CPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. After manually tuning the PBO PPT, TDC, and EDC parameters, we see a performance uplift in most of the multi-threaded benchmark applications. Surprisingly, we find the most significant performance increase in 3DMark CPU profile, which improves 16 percentage points and is now plus 61.86% higher than stock. In Prime 95, we find that tuning the PPT, TDC, and EDC provides additional sustained all-core frequency across the board. The most significant frequency is in the test scenario with SMT and AVX enabled, as we get an extra 337 MHz. Also noteworthy is that we achieve a sustained frequency of 4 GHz with 1.033 volts on all 64 cores when disabling SMT and AVX. The primary limiting factor for the Prime 95 sustained workload is the CPU temperature, which reaches 95 degrees Celsius, and that is the maximum allowed temperature. However, even if we could decrease the CPU temperature, we find that the VRM temperature is already at 80 degrees Celsius and nearing its thermal limit as well. Furthermore, the water temperature is around 36 degrees Celsius, which is also near the 40 degrees Celsius where our fan curve would be at 100%. We're already sporting 2 radiators with 7 fans, making a severe amount of noise. And last not but least, look at those EDC values. When we disable AVX, the EDC is at a sustained 800 amps throughout the entirety of the 30-minute Prime 95 run. I don't think I've ever felt so on the limit with what's probably the world's most powerful desktop system. In our fourth overclocking strategy, we push the Precision Boost Overdrive parameters to their limit and see what peak performance would look like if it wasn't for the VRM limitations. As we saw in our previous OC strategy, we must hard limit the EDC parameter to 800 amps to ensure VRM stability across all benchmarks and stability tests. If we check the behavior in specific benchmarks again, we still hit the maximum EDC in Geekbench 5, Cinebench R23, CPU-Z, Y-Cruncher, and Blender. What may surprise you is that we also hit the EDC limit when disabling SMT. In fact, in all benchmarks bar 3DMark CPU profile, we either get close to or hit the EDC limit. In this overclocking strategy, we simply push the EDC limit as high as it needs to go until it's no longer a limiting factor for our benchmark applications. That appears to be around 1050 amps. Yes, over 1 kiloamp. In fact, we see EDC peak over 1000 amps in multiple benchmarks: Geekbench 5, CPU-Z, Y-Cruncher, and Blender. In addition to increasing the EDC parameter, we also set curve optimizer to -30 for all cores. Again, while this isn't Prime 95 stable, it does seem to pass all benchmarks. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP standard. Set memory frequency to DDR4 3600 MHz. Set if clock frequency to 1800 MHz. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to manual. Set PPT limit to 1000. Set TDC limit to 800. Set EDC limit to 1100. Set Precision Boost Overdrive Scaler to manual. Set Precision Boost Overdrive Scaler to 10x. Set Max CPU Boost Clock Override to 200 MHz. Go to the Advanced menu. Enter the AMD Overclocking submenu. Click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set Precision Boost Overdrive Scaler to Manual. Set Precision Boost Overdrive Scaler to 10x. Enter the Curve Optimizer submenu. Set Curve Optimizer to All Cores. Set All Core Curve Optimizer sign to negative. Set All Core Curve Optimizer magnitude to 30. Leave the Curve Optimizer submenu. Set Max CPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. In the fifth and final overclocking strategy, we finally get to do some manual overclocking. Unlike with the Ryzen Threadripper 5990X, I won't focus on trying to get Prime 95 stable configurations. Instead, I'll focus on optimizing the performance in specific benchmark applications: AI Benchmark, Cinebench R23, and 3DMark CPU Profile Max threads. One could question the use case for manual overclocking the Ryzen Threadripper CPUs. Just like with all Ryzen processors, the major downside of manual overclocking is that you lose the benefits of precision boost technology in low-threaded benchmark applications. However, I believe there is a good use case for manually overclocking on Ryzen Threadripper. The main advantage of precision boost is that it changes the voltage and frequency dynamically depending on the workload. The main disadvantage is that the constant change in voltage is pretty tough on the VRM. As we learned from our previous overclocking strategies, this may even result in system instability when running specific applications. When manual overclocking, you avoid the stress on the VRM from the constant voltage changes. Furthermore, you also limit the maximum voltage to a much lower value than precision boost. Overall, for Ryzen Threadripper, manual overclocking should be more optimal for the VRM. In addition to the reduced stress of the VRM, manual tuning has even more benefits. First, automatic overclocking and frequency boosting techniques always leave a little margin on the table. We can exploit this margin and fine-tune for application stability when manual overclocking with our specific hardware configuration. Second, in multi-threaded applications, Precision Boost Overdrive applies a single frequency to every core. However, on AMD Ryzen CPUs, you can set the frequency for each CCX separately. So, we can exploit the fact that some CCXs may overclock better than others. To better understand the performance tuning opportunities embedded in the Ryzen Threadripper 5990X CPU, let's have a closer look at the CPU architecture. The Ryzen Threadripper 5990X would have been AMD's Chagall Zen 3 based flagship CPU. Chagall is derived from the EPYC Milan server product line and features no less than 9 chips on package, 8 CCDs and a single I/O die. CCD stands for Core Chiplet Die and is just a die on a Ryzen CPU with CPU cores. The Zen cores are packed together in a CCX or core complex. A Zen 3 CCX consists of up to 8 individual cores, each with their L2 and L2 cache and a shared 32 MB of L3 cache. The frequency of the CPU cores is driven by a 100 MHz reference clock input. Each CCX has its own PLL and thus can run an independent frequency. The cores within a CCX share the same PLL, so they'll run at the same frequency. That means for the Ryzen Threadripper 5990X, we can set an independent frequency for each of the 8 CCXs. Ironically, that means we have less tuning granularity than with the Zen 2 Ryzen Threadripper 5990X, as Zen 2 has 2 CCXs in one CCD and does double the amount of CCX frequency tuning capabilities. The voltage of the CPU cores is provided by the VDDCR CPU voltage rail. This voltage is shared across all the CCDs, so each CPU core will be provided with the same voltage. Choosing the right manual voltage is always a trade-off between finding more room for higher frequencies, dealing with all of the thermal limitations, and of course, considering the CPU lifespan. It's with that last thought that we kick off what's arguably the most tedious or exciting aspect of Ryzen Threadripper overclocking, per CCX frequency tuning. Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So, the first step in our tuning process would be to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CPU ratio of each CCX. Simply increase the ratio of one CCX until the application shows signs of instability, then back off. Do this for each CCX sequentially, and you'll end up with the maximum stable per CCX frequency for a given voltage. We do this for every benchmark we include in our manual overclocking strategy. In this table, you can find the maximum ratio for each of the CCXs in each benchmark. Just as a reminder, the values in this table are for my specific system and a specific stability test. Your CPU may have wildly different values depending on the CPU sample, cooling, and motherboard, and your chosen stability test. The AMD Chagall CPU package is divided into 4 equal quadrants. Each quadrant consists of a pair of CCDs with access to 2 linked memory channels. So, in total, Chagall processors offer up to 8 channels of DDR4 memory, half of which are disabled on the Ryzen Threadripper non-Pro processors. Even though that's half of what the Zen 3 Ryzen EPYC server processors offer, it's still double compared to the desktop Zen 3 Ryzen CPUs. On Zen 3 Threadripper processors, there are up to 9 chips on package, 1 I/O die, and up to 8 CCDs. The CCD contains 1 CCX with the CPU cores and an Infinity Fabric connection. All other I/O connectivity, including the memory controllers, is located in the on-package 14nm I/O die. This ensures better overall latency for memory access, but puts the onus on a fast fabric clock to ensure high performance. When a CPU core needs to access data in the system memory, it connects via the Infinity Fabric to the I/O die and then accesses the memory controller. AMD officially supports up to DDR4 3200, but Ryzen CPUs can push the memory frequency slightly higher than that. That said, it's not as easy as it may sound. To make a long story very short, there are 3 relevant frequencies when it comes to system memory performance. M-clock, or memory clock, is the frequency of your DDR4 memory. U-clock, or memory controller clock, is the frequency of the integrated memory controllers. F-clock, or fabric clock, is the frequency of the Infinity Fabric. The system memory and memory controller frequency are driven by the same 100 MHz reference clock used for the CPU cores. The memory controller and memory frequency are tied together. You can run both at the same frequency or run the memory controller at half the system memory frequency when memory gear down mode is enabled. The voltage of the memory is provided by 2 VDDIO MEM S3 voltage rails. Each voltage rail powers the memory linked to a specific memory controller. The voltage for the memory controller and fabric is provided by the VDDCR SoC voltage rail. We continue to use our XMP memory timings and voltage, but change the XMP frequency from DDR4 4266 to DDR4 3600. When the CPU cores want to store or retrieve data from the system memory, it does this via the Infinity Fabric and the memory controllers in the IOD chip. By default, these 3 parts are running in sync, meaning they all operate at the same frequency. When overclocking the system memory, you can choose to use it in synchronous or asynchronous mode. Synchronous mode is relatively taxing for the CPU, so on most Ryzen CPUs, the system will automatically enable asynchronous mode beyond a particular memory frequency. As the memory overclocking capabilities of the Chagall processors are relatively limited, not in the least because of the 4 memory controllers, we prefer to run in synchronous mode. The fabric clock frequency is driven by the same 100 MHz reference clock used for the CPU cores. It can be clocked independently from the CPU cores, memory controller, or memory frequency. The fabric voltage is provided by the VDDCR SoC voltage rail, which also powers the memory controllers. For Zen 3 processors, generally, synchronous mode will work all the way up to DDR4 3600 and a fabric clock of 1.8 GHz, though some people might see higher frequencies. For example, I was able to get 1.867 GHz on this CPU. Now that we know the ins and outs of Ryzen Threadripper 5000 overclocking, let's get to work. Let's do some manual overclocking. For this guide, I will show you the settings for AI benchmark, which is a heavy multi-threaded benchmark that doesn't really scale that well with SMT. Upon entering the BIOS, go to the AI tweaker menu. Set AI overclock tuner to DOCP standard. Set memory frequency to DDR4 3600 MHz. Set F-clock frequency to 1800 MHz. Enter the CPU core ratio per CCX submenu. Set core VID to 1.275. Set CCD0 CCX0 to 43.25. Set CCD1 CCX0 to 43. Set CCD0 CCX0 to 41.75. Set CCD3 CCX0 to 41.75. Set CCD4 CCX0 to 43.75. Set CCD5 CCX0 to 42.75. Set CCD6 CCX0 to 41.75. Set CCD7 CCX0 to 42.25. Leave the CPU core ratio per CCX submenu. Go to the Advanced menu. Enter the CPU configuration submenu. Set SMT mode to disabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. The performance improvements from manual tuning in the 3 benchmarks range from 1% to 11%. Ultimately, the headroom boils down to the characteristics of the specific workload. Oh, and yeah, that's 100,000 points in Cinebench R23 with a single socket water-cooled CPU. In a benchmark like AI benchmark, which heavily relies on AVX acceleration and has a mix of single-threaded and multi-threaded aspects, you'll find that the precision boost algorithm is pretty good at maximizing the performance. When manual tuning, you can increase the multi-threaded performance, but will not be able to match the single-threaded frequency boosts. In a benchmark like Cinebench R23, a heavy multi-threaded workload, you'll find that exploiting the margins through manual tuning can yield an additional 5% performance. The main limitation will be your cooling solution, which restricts the maximum voltage and associated stable operating frequency. In a benchmark like 3D Mark CPU Profile, a light multi-threaded workload, you'll find that a superior cooling solution will provide maximum thermal headroom. This enables much higher operating voltage and thus higher frequency. You can increase the frequency beyond the artificial precision boost frequency limit by manual overclocking. Therefore, you can achieve additional performance improvements of over 10%. Alright, let's wrap this up. I had the unique opportunity to check out what a consumer variant of Zen 3 Ryzen Threadripper would look like. Since this is an early engineering sample and a beta BIOS, I would take the performance with a grain of salt. However, the overclocking experience should translate quite well to final silicon. The first point I want to make is that this is undoubtedly the most powerful desktop I've ever tried and I've ever seen. I mean, when you truly unleash the performance of Ryzen Threadripper 5000 through overclocking, you push everything to its limit. The motherboard VRM, the liquid cooling solution, the power supply, and of course the compute performance. I mean, holy f***, you get 100,000 points in Cinebench R23 with one CPU and regular water cooling. Not LN2, regular water cooling. The second point I would like to make is that I do sympathize with the people who would love to see this kind of a consumer variant of Ryzen Threadripper Zen 3 for it to come to market so that they can maybe upgrade their system. But I do see some issues. The first issue I would see is that the performance of this 5990X was not that much higher than the performance that I saw with the 3990X. And from what I can see, that's primarily because the precision boost parameters are aggressively capping the frequency, especially in multi-threaded workloads. Of course, you can work around that by enabling precision boost overdrive or even manually tuning those settings, but that requires a really good cooling solution and you need a really good motherboard VRM. So I'm a little bit worried that the existing motherboards on the market may not have the overspec VRM you'd need for Zen 3 Ryzen Threadripper. And in line with that last thought, I think we also need to start looking at liquid cooling first motherboards. Of course, there are already quite a bunch of motherboards on the market with liquid cooling in mind, even motherboards that come with liquid cooling solutions in the motherboard box. But more often than not, those solutions prioritize aesthetics over cooling performance or even cost. A CPU like the Ryzen Threadripper packs a tremendous amount of performance, but to unleash it in a reliable way, you definitely need an overspec VRM and you definitely need liquid cooling. All right, well, that's it for today. I thank you for watching. I also want to thank my patrons for the support. If the professional Ryzen Threadripper 5000 CPUs eventually come to market for DIY and become overclockable, I might have a look at those. If not, my next AMD CPU video will probably be sometime in September. As per usual, if you want to check out my settings or my specific results, I'll also put up a written version of this video on my blog. If you have any questions, feel free to drop them in the comment section below, and see you next time.